So in this section, we're going to cover compound interest. And the way compound interest varies from what we saw earlier in simple interest is compound interest, you put down a principal, and after a certain period of time called the compounding period, you apply the interest to the principal. Then that interest is the new starting balance for the next compounding period. So over the next compounding period, you get interest on the original principal plus the interest you gained in the last compounding period. This keeps going on, so the amount that you're getting interest on keeps growing, and that leads to exponential growth over time. So we have two formulas for compound interest. The first one is if you have compound interest once a year, think annual. And then the next one is compound interest for in compounding periods a year. So for instance, if they say monthly, then in is 12. If it's compounded daily, then in is 365 because there's about 365 days in a year. Don't worry so much about leap years. We're not getting that granular here. Or if they say weekly compounding, there's 52 weeks in a year. So just based on how they describe it, however many times it's compounded, that becomes the n. And notice the n in this case divides the interest rate. R is the percent interest as a decimal in both formulas. P is the original principal. And the one thing I'd caution you all about here is we're going to need to be careful with our exponents when we're working with your calculator. I'll try to show that and model that as I work through this. But I would encourage you maybe to just put this in parentheses right now to remind yourself this whole number of compounding periods times time should be kept in parentheses when you type this into your exponent. So let's work through this first example. It says you deposit $2,000 in a savings account and it has a rate of 6% growth. After 3 years with annual compounding, find the amount that we're left with. So really quick, think which formula is the quickest application here. Since it's annual compounding, we're going to go with the first formula. The second one would work with the n of 1, but it's needlessly complex. So we know our principal, I think it can be helpful to write these out. The principal is 2,000. My interest rate as a decimal, well, 6% gets turned to a decimal. Find the decimal place. Move 2 places to the left. It's 0.06. My time is 3 years. So I'll fill in my formula. 2,000 times 1 plus 0.06 with the exponent of 3. And while you don't have to write this down, you could technically type it all in your calculator. Especially as you're getting used to these formulas, I encourage you to write it down exactly so you have something to reference as you're typing everything into the calculator. The most common error at this section will probably be calculator error, so that's what we really need to guard against. So we'll need to have a calculator that allows us to use exponents. For my calculator, the exponent looks like it's here. For some of y'all, you might see something like this as the exponent button. If you can't find the exponent in your calculator, send me a picture of yours and I'll be happy to help find it. So for my calculator, I'm going to deal with this portion first and then multiply by 2,000. I'll type in the 1 plus 0.06. So that's the inside of the parentheses. And now I want to exponent that to 3, so I'm going to do exponent 3. And then this amount is what I need to multiply by 2,000. When the numbers are written next to each other with no sign, that's implied multiplication. And I'm going to round all of these to 2 decimal places, so we get around 238203. So that's the amount balance after 3 years. And then if we're asked to find the exact interest, that's the amount minus the principal. So 2382.03 minus the original $2,000 we put in will give us $382.03 as the interest only. So let's look at our next example here. We deposit $7,500 in a savings account. Suppose we get about 6% compounded monthly. We want to find the amount after 5 years and then the interest after 5 years. So let's go back to our original formulas. Since we're compounding monthly, which of these two should we use? Okay, we should use this formula, and we should use n is 12 because it's monthly. So that we don't have to keep changing the screen, I've just copied that here in the highlighted box below. So I'd give y'all a chance to pause this and attempt this problem on your own. Write out the formulas and then use your calculator. Unpause to check your work. So we will start by identifying the different parts of our formula. The principal is equal to $7,500. My interest rate, we calculated this before, is 6%, so that's 0.06. I believe same as our last example. We know since it says compounded monthly, our number of compounding periods is 12 in 1 year. And our time, they said 5 years, so that's going to be 5. Now I'll write it into this formula. 7,500 times 1 plus, 0.06 over 12. So that's the fraction. And then my exponent I'm going to write in parentheses to make sure I type it that way in the calculator. N is 12 times t of 5. So let's bring our calculator on screen. And just a hint to everybody, the key things that you want here is these need to be grouped together, these need to be grouped together, and then at the end we need to multiply this times this. This is in the exponent position. So that's what we want to make sure we type into our calculator correctly. I also recommend putting parentheses on the top and the bottom there for our fractions so that it doesn't mix anything up. And if you have a particularly capable calculator like a TI-84, 89, some of these are overkill. I'm talking about for some of the more simple calculators, you have to give a bit more instruction when it comes to setting up the expressions. So for my calculator, I'm going to multiply by 7,500 at the end so that I can focus on these details first, typing into my calculator. So I first need to figure out what is on the inside of this parenthesis, and then once I get all of that, then I'll raise that to the exponent. Once I get that value, then I'll multiply that by 7,500. So that's my process, my parentheses for the first one. 1 plus, now I'm going to set up my division, parentheses, 0.06, close parentheses, divided by, open new parentheses for the bottom, 12, close parentheses. Now that's closing this parentheses, and then I'm going to close this one to keep the whole inside together. Notice if I write out the parentheses, I can just read kind of left to right. It keeps track of things for me. So that's the value. 1.005 is what all of this is equal to. That needs to be raised to this exponent. So I'm going to do exponent, parentheses to make sure the whole exponent stays together, 12 times 5, close parentheses. That's what this whole portion is, and now I multiply that by 7,500. And that will be 10/116 point, rounding to 2 decimal places because it's money. The value after is 6, 5 or greater rounds up, less than 5 stays the same, so that'll be 0.38. And then to find the interest accumulated, we take the amount that we've earned, or the total amount in the account after these years, subtract the original amount that we put in to the account, and we should get $2,616.38. So in this example, we're going to show step by step how this compounded interest works for a 5-year period. So we're going to consider $5,000 invested at 5% compounding annually here. So our starting balance is $5,000, and maybe we can draw down these little column lines to help keep things straight. So if we wanted to find the interest on this, going back to our simple interest idea, we would just say, okay, the way you calculate interest is you take the principal times, or the amount gained after interest, 1 plus the rate, and that's what we find here. So for us, that's $5,000 times 1 plus, okay, 5% as a decimal, find the decimal place, move it twice, 0.05. If you type this into your calculator, we will get 5,250. And one quick pause here. You could use the compound interest formula we showed on the first page of this section of notes. What I'm doing right now is showing why we call it compounding interest, because we compound each new year balance. So this is kind of showing how it works behind the scenes. But if you were wanting to compute this efficiently, you would just use this formula, because this is an annual, and we would do at the end 5 years. So keep that in mind. This is the efficient way. We're kind of showing what's happening behind the scenes. So for the next year of growth, we no longer are just getting 5% interest on this $5,000. We're getting 5% interest on this new value, 5,250. So then to use that formula, that becomes your new principal. And we would get $5,512.50. And then for year 3, that becomes the new principal that we gain interest on. So each year, the principal that you gain interest on grows, so the interest grows each year. So it gets bigger and bigger and bigger and bigger. And that's why it's important for compound interest for savings to invest early and keep investing over time, and the amount of interest that you gain year over year will grow. So this next one becomes this value. Let's round to 2 decimal places. That 5 is 5 or greater, so we'll round this up to a 3. 5788.13. And now this new value becomes what we get 5% interest on. Type this into our calculator, and we get $6,077.53. When I round to 2 decimal places, this 6 or greater will round this up to a 4. And then to calculate the amount in our account after the 5th year, we bring our new principal down, find the interest on that principal after 1 year at 5%. And when we round this to 2 decimal places, this 7 is in the 5 or greater category, so this rounds up to 42. So 6381.42. And that will be the amount of money in our account after 5 years. And if you calculated the amount of interest gained year after year, you'd see that the amount of interest gained each year keeps growing, because the principal that you're drawing interest from keeps growing due to our compounded interest idea, that each year's balance becomes a new thing that you're calculating interest on, repeated year after year after year. So in the last example of this section, let's do an investment comparison. We have $8,000 to invest for 6 years, and we're considering 2 different options. Account 1 will pay 7% and compound monthly, whereas account 2 pays a slightly less percentage and compounds annually. So we need to determine which is a better investment. So we need to calculate the value in each account at the end of 6 years. Whichever one has a higher yield, we'll pick that one for us. So let's look at we know this is our compounded interest formula for a various compounding period N. So for account 1, if it's compounding monthly, N is 12. Now if we're compounding annually, we can use this formula when N is equal to 1. But if you go back to the first page of these notes, you can find a more efficient formula to use as well. Both will work. But if you prefer, you could just use the formula A equals P times 1 plus R over T. It's the exact same formula as this when N is plugged in for 1, but you might find this a little faster to type in because you don't have to realize that R over 1 is just R, 1 times T is just T. So I'd encourage you, pause the video and find the account balance for option 1 and option 2, and then unpause to check your work. So here for account 1, my interest rate as a decimal is 0.07. The number of compounding periods is 12. The amount of time in both cases is 6 years. And my principal, I was investing $8,000 in both accounts. So here they have this A subscript 1. This just indicates the account balance in the first account, whereas A subscript 2 is the account balance in the second account. So writing in my formula, I'll get 8,000 times 1 plus 0.07 over 12, close parentheses, 12 times 6. And now personally, I'm going to write all the parentheses that I need to type in to my calculator so I don't forget it. I'm going to do a parentheses in the top fraction and the bottom fraction to keep everything in the top together, everything in the bottom together. I'm going to do parentheses around the exponent to make sure I keep these as an exponent. And if it helps me, I can write a common symbol for exponent, my exponent button here. I know that I'm going to find this value first, then raise that to the exponent, and then take this overall value and multiply by 8,000. So let's do that in our calculator. So parentheses 1 plus, okay, now I'm going to type this open red parentheses. I'm just typing what I see. Close parentheses, divided by for the fraction, open parentheses for the bottom, close the red parentheses for the bottom. Now I need to close the overall parentheses for this entire term. And that's what I get. And then I raise this to the exponent, 12 times 6 years. That's what I get for this whole term. Then this needs to be multiplied by 8,000. Do be careful. Don't round intermediate steps. If you round intermediate steps, your value will be slightly off, where it could be enough off that you get the wrong answer. So without rounding at intermediate steps, using the whole value as I make the next calculation, we get 12,160.84. Rounded to 2 decimal place. Since the third decimal place is less than 5, it stays the same. So we get that value. Now let's look at the second account. So now with the second account, if we look at the details provided above, we know our interest rate for this one is 0.0685 when you move the decimal place 2 places to the left. Since it's compounded annually, we know our N is 1, our amount of time is still 6 years, and our principal, I'll add that in, is 8,000 as well. So we could use this formula with just an N equal to 1, but we could also use the formula just for annual compounding, and that is P times 1 plus R to the T. So substituting in our values, we get 8,000 times 1 plus 0.0685 to the T of 6 years. Let's type this into our calculator. So 1 plus 0.0685 raised to the exponent of 6 years gets me this value times 8,000. And we get 11,905.21 when we round to 2 decimal places. And now we need to compare the two. Which one will give us a larger value? Account 1 will, at the end of the 6-year period of time, result in a larger overall value. So as we looked at this compound interest, so far all the examples have been towards investing. However, debt can also grow at a compounded rate. So it's important to realize that compound interest can either grow and make you more and more money through investments, or it could grow and make more and more money that's owed due to debt. So just an important thing is the power of compounding over time can lead to significant financial growth or debt, depending on whether you're the lender or the borrower. So if you have any questions about this section, please do reach out to me. I'll be happy to answer, and we'll see you in the next section.